Exercise 13.21 just explores a couple ways that you can do elimination reactions with alcohols. So you could start with an alcohol, look at the OH of the alcohol, and eliminate it. Remember that in elimination reactions, you remove something from a molecule, and you create a pi bond. Okay, now this first example, using concentrated sulfuric acid and heat, is a sort of unique, almost a kind of exception among the elimination reactions. Usually with elimination reactions, you will recognize them because you add a base. And this OH will have to leave, and then the base will steal what's called a beta hydrogen. Now, I'll walk through this in some detail in this video, but the truth is, if you want a really strong foundation in elimination reactions, I strongly encourage you to watch the review videos that I've posted in the playlist for the Organic Chemistry 1 review for this class. Okay, so what happens? Well, we want this OH to leave, so we have to turn it into a better leaving group. We've seen in the previous video how an OH is not a good leaving group. That's where this sulfuric acid comes in. Sulfuric acid looks a little bit like this. You've got sulfur double bonded to oxygen above and below, single bonded to oxygen on each side, and then it has hydrogens on those oxygens on each side. So that's sulfuric acid. Now, the oxygen in this alcohol is slightly negative, and so it will be attracted to the slightly positive hydrogens in sulfuric acid, and it'll attack them. So it attacks that, the electrons snap back onto the oxygen there. And so after this first step, what was an OH, and here I'll just separate this other H so that it becomes a little bit clearer. What was an OH becomes, oops, really an H2O with a full positive charge. And we've seen this in a previous video, even just for this chapter. By adding that H plus there, by doing this proton transfer, transferring a hydrogen from one molecule to another, you turn a bad leaving group into a good leaving group. This is now, if this leaves, takes these electrons and leaves, it leaves as water, which is very stable. And so that's really what that does. You do the proton transfer to turn this into a better leaving group, and then it leaves. Here's loss of a leaving group. Oops. That the electrons in that bond becomes a new lone pair. That stabilizes what was the positive charge, and that goes off to live its best life, the water molecule there. Now, the carbon, this carbon lost the electrons from this bond, so it has a full positive charge now. It's a carbocation. Okay, next thing. I've kind of been ignoring what happened to sulfuric acid. It lost its hydrogen. So I'm going to redraw that here. This hydrogen would have gone away. These electrons would have gone on this oxygen here, and that oxygen would have a full negative charge there. And so that hydrogen sulfate, as it would be called, that is a weak base, but it can function as a base. And that's how we're going to form the pi bond in this elimination reaction. Okay. Now remember, elimination reactions depend on the beta hydrogens. The beta hydrogens, the carbon that had the leaving group on it, the carbon that has the carbocation on it, is the alpha carbon. And every carbon next to it is called the beta carbon. So we have 3 different beta carbons here. Each of the hydrogens on those beta carbons are vulnerable to an attack by a base. Now before I draw this in, I just want to point out this methyl group on the end and this methyl group on the end are in symmetrical positions. There's sort of a line of symmetry down here. And so I'm only going to consider one of them because whatever happens to one equally represents what could happen to the other on the other side of that line of symmetry. Okay, so I'm going to draw just one hydrogen on each of these beta carbons. There are more there. There are 3 hydrogens on the beta carbon to the left, and there are 2 on the beta carbon to the right, but I'm just going to draw one so that we can see what happens to that one. Okay, so those are vulnerable. Now, our base can swoop in, and it can attack either one of those. So on the one hand, the base can attack the beta hydrogen here. The electrons would be pulled toward the positive charge of the carbocation, and we could get this molecule with a pi bond between the alpha carbon and the beta carbon that the hydrogen was stolen from. That's one possible result, one possible product. On the other hand, this hydrogen sulfate could steal the other beta hydrogen. It could act as a base and steal this other hydrogen, and these electrons can go toward the positive charge, and you would have a different product. So these are 2 possible products you could get by just treating that original molecule with concentrated sulfuric acid. And that's often the case with elimination reactions. There are often more than one beta hydrogen. And so there are often more than one places where you could form a pi bond. So oftentimes in elimination reactions, you get a mixture of products. And if a mixture of products is ever possible, then you always get both or all of the different types of products. So you always get all of the different types of products. But there's a difference between whether you get the majority, but there is sometimes a difference between how much of each product you get. Okay, to discuss that more precisely, we have to look at these double bonds and sort of classify them. Let's look at this double bond on the left. Look at the 2 carbons in the double bond and ask yourself how many carbons are the carbons in that double bond bonded to total. This one on the left and you're not counting the one in the middle, so going away from the double bond. Now this one on the left is not bonded to any. There are no carbon branches coming off of that. The one on the right is bonded to 2. However many carbon branches are coming off of those 2 orange dots, that's how substituted the double bond is. So here, none, none, 1, 1, that's a total of 2. This has 2 carbon branches coming off of the double bond. The double bond is described as di-substituted. On the other double bond, look at the 2 carbons in the double bond. Ask yourself how many carbon chains are coming off of those. Here we have on the one on the left, 1, 1. On the right, 1 and none. We have a total of 3 carbon chains coming off of those. So this is described as tri-substituted. So di-substituted and tri-substituted. The more substituted the pi bond is, the more stable it is. Now I'm going to use a jargon term. That's because of something called hyperconjugation. And I have a video that discusses why that is in the review for Organic Chemistry 1. I think if I go into that here, it's getting a little bit off of track, and it'll make this video a little unnecessarily long. But I strongly encourage you, if you're not familiar with that, to review that from the Organic Chemistry 1 review playlist. So the one that's more substituted is actually more stable. It's called the Zaitsev product, the more substituted product. It doesn't have to be tri-substituted, it just has to be the more substituted of the different options. That's the Zaitsev product, and you can make that one your major product if you use a skinny base. that's for E2 reactions. We'll discuss that in a second. But usually a skinny base is associated with the Zaitsev product. The less substituted product, and it doesn't have to be di-substituted, it just has to be the less substituted of your different options, that's called the Hofmann product. And in an E2 reaction, and again, we'll discuss what that is in just a second, you would use a bulky base to get that. So an example of a bulky base is potassium tert-butoxide. You would have seen that as TBUOK in Organic Chemistry 1. You have a tert-butyl group, and if you're not familiar with the common names of some strange branches, that's another thing that'll come back in a lot of chapters. So I encourage you to watch the video I have for that available on the Organic Chemistry 1 review playlist. That's this TBU, tert-butyl group. Then you have an oxygen. This oxygen has a full negative charge, and the potassium is balancing that charge out with a full positive charge. That's potassium tert-butoxide. It's a bulky base that will make you favor the less substituted elimination product in an E2 reaction. Skinny bases are anything that have an oxygen with anything with a small side chain. So for example, if you have an OH with a negative charge, it's really small, skinny. If you have an OMe, that's a methyl group, that's a small group. If you have an with an ethyl group, that's really small. So any of these are skinny bases, and those are usually balanced out by sodium, but really they could be balanced out by any positive ion, lithium, potassium. So that would look like something like NaOH, NaOMe, NaOET. And hopefully this is a review really from Organic Chemistry 1, and seeing these structures, you get a warm sensation around your heart. It's like looking at old friends. Okay, well these are for E2 reactions. Notice that when we did this mechanism, we showed two things. We showed loss of a leaving group, and we showed this proton transfer. Now in this case, only one of those ever happened at a time. We had loss of a leaving group, full stop. Separate from that, after that, we had this proton transfer that created the pi bond. And then that happened. So only one thing ever happened at a time. So this reaction, when you use concentrated sulfuric acid and heat, that reaction is called an E1 reaction. It's called an E reaction because it's an elimination reaction. You start with an OH on the molecule, but you end up with no OH on the molecule. So it's an elimination reaction, E, and only one thing ever happens at a time. Loss of a leaving group happens, and then separately from that, proton transfer happens. And so only one thing happens at a time, it's E1. Okay. In an E1 reaction, your major product is always the more stable, more substituted Zaitsev product. So let me draw these two products, copy and paste these, where we're predicting our answer. And these are two products. We're going to get both of them, but because this is an E1 mechanism, and that will always be true when you use concentrated sulfuric acid and heat, the more substituted product, here this tri-substituted one on the right, is your major product. And the less substituted one on the left is your minor product. And these are things that you will want to have, that you will need to list on a test question. So if you had something like this on a test question, you would want to draw both of the possible elimination products and say which one is the minor product, which one is the major product. And you would go through that process that we went through before of figuring out which one is more substituted. That's the Zaitsev product. That's the major product for an E1 reaction. And then which one is less substituted? That's the Hofmann product. That's the major product for the major product. Well, that's the minor product for an E1 reaction. Okay, so much for A. Let's sort of take this same thinking and apply it to B. All right. Now in B, so we'll use concentrated sulfuric acid and heat to do an E1 reaction. How can we do an E2 reaction? That's the type of problem that we approach in B. Now we're still doing an elimination, so we still want to get rid of that OH, and we're still going to end up with a pi bond somewhere. To get rid of the OH, we have to turn it into a good leaving group because the OH by itself is a bad leaving group. If it tries to leave, it's an OH minus. It's a hydroxide ion, which is a strong base and a strong nucleophile, really just unstable. So what we'll do is we will take that, and this TSCl is a really big group. TSCl is a large structure that really turns that into a good leaving group. So we don't have to wade into the structure for that here. I do have several videos from Organic Chemistry 1 that walk through how that acts, how that turns this into a good leaving group. But it's a large molecule, and you do an SN2 reaction. This PY pyridine is there to take the H off. That should all seem relatively familiar from what we've discussed in the last couple of videos. Ultimately, that first step, TSCl and pyridine, that first step replaces the hydrogen with what's called a tosylate group. So this is called tosyl chloride. And you have this tosylate group. And the thing to remember about the tosylate group is that it's a good leaving group. And I might make a small video that walks through tosylate groups, but they're really kind of a sidebar. They're not something that appears too often, although they're important to do these E2 reactions with alcohols. Okay, so the important thing to know is this first step replaces the H with a tosyl group, and now this is a great leaving group. All right, so now that we have a good leaving group, we can start to think about the elimination reaction. We look at the carbon that has the leaving group on it. That's the alpha carbon. Each of the carbons bonded to that is a beta carbon. The hydrogens on the beta carbon are the hydrogens that are vulnerable to attack from a base. Now, if you can only do an E1 reaction if the leaving group is on a tertiary carbon, because that gives you a stable tertiary carbocation. If the leaving group is on a primary or a secondary carbon, then you're going to do an E2 reaction. And so the loss of the leaving group and the proton transfer will happen at the same time. Also, with an E2 reaction, you have to consider what type of a base you have, a bulky base or a skinny base. Bulky bases will prefer the less substituted Hofmann product, and skinny bases will prefer the more substituted Zaitsev product. Now, there are a lot of exercises I have from Organic Chemistry 1, videos that walk through exercises that explore that concept in more detail. So here, I'm just going to touch on it briefly, but if you're not familiar with that part of elimination reactions, for this test, you'll definitely want to be able to distinguish when you'll get the Zaitsev product and when you'll get the Hofmann product. And I have a video that walks through how to do that in the review playlist for Organic Chemistry 1. So here we have sodium ethoxide, and what that looks like is you have an oxygen with a full negative charge and an ethyl group. That's ethoxide. And that's being balanced out by the positive charge on the sodium. So that's what this NaOET is. The ET is an ethyl group. So this oxygen can swoop in, steal one of these hydrogens. Notice that there's symmetry in this molecule. So both of these hydrogens, whatever happens to one, that's all that could happen to the other one too. So we're just going to look at one of these. It can swoop in, the electrons would go toward the leaving group and kick the good leaving group off. Notice how you have proton transfer and loss of a leaving group happening at the same time. That's what makes this an E2 reaction. You're eliminating the OH, and two things are happening at the same time when you do that. And the result is that you form a pi bond there. Okay, now that, oops, and then this tosylate group isn't there, the bond that's there isn't there anymore. Now that's the only possible product here, because we only had one unique beta hydrogen. So that's the only possible elimination product here. I do want to point out, though, that when you do these E2 reactions, and even sometimes if you'll do the E1s, but really for this chapter, for the E2 reactions, you'll want to review a table from Organic Chemistry 1 that discussed in detail from Chapter 8 of Organic Chemistry 1, from the elimination, and at the end of the Elimination and Substitution chapter, you would have discussed how the overlap, the sort of Venn diagram between those types of mechanisms, how you could have a leaving group on a primary, secondary, or tertiary carbon, and how you could have different reagents that are different types of bases or nucleophiles. Now, when you do these E2 reactions, you're either going to use potassium tert-butoxide or these other alkoxides or hydroxides. You'll notice that on this table, those are all strong bases and strong nucleophiles. And so, if you have the leaving group on a primary or a secondary carbon, those don't just give you the E2 product like we drew, they also will give you the SN2 product. So you'll want to be familiar with these. You'll want to be able to know that, to draw both of those products and to label each one as major or minor. So we drew this elimination product, and that is one that you would get here. But another possible one, another possible product, is if you had these two reagents, instead of doing this elimination, another reaction that also happens in the same beaker is the substitution reaction. And that is where this swoops in, attacks that carbon, and kicks that leaving group off. And that would replace that tosylate leaving group. And so that would be the substitution product. And really that's an SN2 product. You have the nucleophilic attack and loss of a leaving group happening at the same time. So these are our two products here. This is our E2 product, our elimination product. This is our substitution product, our SN2 product. If you notice the leaving group was on a carbon that was bonded to two other carbons. So that is, the leaving group is on a secondary carbon. That means that here, our E2 product will be our major product, and the SN2 product will be the minor product. So this will be the major product, and this will be the minor product. If the leaving group were on a primary carbon, it would be the other way around. Okay, now this exercise sort of walked through how you could do an E2 mechanism. You could do an E2 elimination reaction with an alcohol, first by using a tosyl chloride and pyridine, and second by using a base. This exercise only showed you a skinny base, but you'll want to know what would happen if you used a bulky base. Now that's the reason why this chapter didn't include that specifically in this reaction is because that's really review. You would have spent a whole chapter talking about that in Organic Chemistry 1. So if you're not familiar with this, it's a Hoffman and Zaitsev product, bulky base and skinny base thing, I strongly encourage you to review videos from the previous chapter because that is something that would be fair game on this test. The other thing you'll want to review here is just being able to know that when you use these oxygen nucleophiles, that you don't just get the elimination product, you also often get the substitution product. You want to be able to draw that also, and to label each as major or minor. Okay, so this is the general idea behind elimination reactions of alcohols. You could have E1 reactions, and really we'll just be doing that with concentrated sulfuric acid and heat. You want to draw all of the products for that, major and minor, and be able to label the major and minor product. Remember, the Zaitsev more substituted product is always the major product for an E1 reaction. Notice that you don't have to draw this mechanism. I'm drawing that there so that I don't just show you the answer and say accept it. I'm showing you like how that happens. That's why I've drawn all of this. But on the test, you wouldn't have to draw this whole mechanism. You would have to predict the correct products and say which one is major or minor. That's with concentrated sulfuric acid and heat for an E1 reaction, and for an E2 reaction, you'll always have this tosyl chloride and pyridine as your first step that turns the alcohol, the OH, from a bad leaving group into a good one, a tosylate leaving group. And then you would follow that up either with a skinny base if you want to get the Zaitsev product as your major product, or the bulky base if you want to get the Hoffman product as your major product. And always watch out to include the substitution products if you'll get those. If you get those two in the reaction. Now I may append a little video to this, I have to think about it, I may append a little video to this that walks through the tosylate and how that first step, the TSCl and pyridine, turns the OH into a good leaving group, just to be more convenient so you don't have to sift through those older videos. Just in case you're interested, I did decide to walk through very quickly how the mechanism behind that tosyl chloride, just for your convenience, so that you have it attached to this video. You don't have to search through older videos I made for Organic Chemistry 1. So what'll happen with this is what this TSCl, it's called tosyl chloride. It looks like this molecule here. So this whole part is the tosyl, and then of course the chloride. You'll notice that this is always paired with this PY, which is pyridine, which we've seen in previous reactions for this chapter. Now look at this sulfur here. Notice how many other electronegative elements it's bonded to. The oxygen on the top pulls electrons away from it. The oxygen on the bottom pulls electrons away from it. The chlorine to the right pulls electrons away from it. And so that sulfur is really slightly positive. And so it's very attractive to the oxygen on an alcohol, which is slightly negative. So that can swoop in and attack that sulfur and break one of the weakest bonds, the pi bonds. So you have that sort of nucleophilic attack there. Remember, our goal with this TSCl is to replace this bad leaving group with a good leaving group. Okay, so what we have at this point is, and here actually I'm going to take this molecule, copy that, we'll have that down here. The pi bond breaks, the electrons go onto that oxygen. So that oxygen now has 3 lone pairs and a full negative charge. And we'll have a new bond to the oxygen of the alcohol, which still has a hydrogen on it and also has whatever carbon chain was there. So it's a big crowded thing right now. Now, this oxygen is very unstable, flapping around in the wind like that with a full negative charge, so it swoops back down, recreates the pi bond, and it does this because this sulfur has a really positive charge still, right? It's losing electrons to a chlorine and 3 oxygens. So this has a very slightly positive charge on it that attracts this negative charge on this oxygen, swoops back down, recreates the pi bond, and kicks off the best leaving group, which is the chlorine. So at this point, the molecule that we have, would look like a little bit like this. So this chlorine is now, chlorine is now a chloride ion with a full negative charge. I'm going to write that alcohol on this other side. Also, one thing I should have mentioned before is this oxygen has 3 bonds and therefore a full positive charge here. Okay, so the chlorine has left, and now this oxygen is kind of unstable. That's the reason why the tosyl chloride is always combined with pyridine. And the name for this is pyridine. This pyridine can act as a base. That nitrogen with the lone pair can accept H pluses. So it can act as a base, steal this hydrogen, the electrons snap back onto the oxygen to stabilize the positive charge. So that overall, what you would have accomplished is where you had an OH, you now have this TSO, right? This is the tosyl group, that we summarize as TS. So the way we write that just quickly is to have the capital TS and then the O, and there it is. And so it's a good leaving group. The reason why this is a good leaving group is because if this bond breaks, if this oxygen leaves, for whatever reason, let's say a nucleophile comes in and pushes it off. Oops. If it leaves, the oxygen there has a full negative charge, and the lone pairs that are carrying that negative charge are allylic. They're one atom away from an atom in multiple double bonds, right? So this lone pair here can exist in a p orbital. In order to have the pi bonds there, you need p orbitals. And then here, there are also parallel p orbitals to create those pi bonds. And so this negative charge can really spread out over almost every atom in this molecule. And so that stabilizes it. Remember, when you spread charge out, it's like diluting it in space, and it becomes more stable. And any molecule that can come off of another molecule and be really stable is a good leaving group. So that's sort of the mechanism behind how this TS, this tosyl chloride, and pyridine can turn an alcohol, which is a terrible leaving group, into a tosylate, which is a much better leaving group here.